Well, welcome to another QHSE Talks. Today we are taking a massive stack of sources. We've got the ASP examination blueprints, the Bechtel rigging handbook, OSHA construction safety regulations, and some incredibly detailed engineering calculation notes. And we are unpacking ASP 11 Domain 1 Topic 2.
Which is a heavy one, pun intended.
Definitely. It covers rigging and load calculations. Our mission today is to really pull back the curtain on the intense mathematics-driven world of lifting heavy objects.
It's so much more than just hooking things up.
Exactly. We're taking these complex engineering concepts and turning them into practical, life-saving knowledge that you can actually use, whether you are prepping for your certification or, actually standing under tons of suspended steel.
And I think a common misconception we run into is this idea that rigging is just a purely physical manual trade.
Like, it's just about brute strength.
Right, like people picture rugged individuals just wrapping chains around steel beams and giving the operator a thumbs up. They assume it's done by feel or by gut instinct honed over years of experience.
Which, experience is great, but
when you look through the Bechtel rigging handbook or the OSHA standards, you realize it is a deeply, ruthlessly analytical discipline.
yes.
Every single lift is governed by a matrix of geometric, dynamic, and environmental forces. If you don't respect the math, experience simply won't save you.
So true. So the very first step in any rigging operation, long before a crane operator even thinks about turning the ignition, is knowing exactly what you're dealing with.
You have to know the weight.
Right. You cannot lift an unknown variable. You have to determine the true weight of the load. And the fundamental equation staring at us from these engineering notes seems elegantly simple at first glance. It basically states that weight equals volume multiplied by density.
Simple on paper, yeah.
Exactly.
But it looks simple, and then it is incredibly unforgiving in practice. The foundational rule across all our sources is that guessing the weight of a load is never acceptable. Ever.
You can't just eyeball it.
No, you cannot just look at a piece of machinery and estimate. You have to calculate the physical space it occupies first, its volume. And out in the real world, industrial loads almost never come in perfectly simple, solid shapes like a child's building blocks.
Yeah, if you're lucky enough to be lifting, say, a solid steel cylinder, the math is pretty straightforward, right? You figure out the area of the flat circular end and just multiply it by how long the cylinder is.
Sure, that's basic geometry.
But industrial loads are rarely solid blocks. What if you're lifting a massive section of industrial piping? It's a cylinder, sure, but it's entirely hollow inside.
And that completely changes the calculation. You can't just measure the outside dimensions and call it a day.
Because then you're calculating for a solid log of steel.
Exactly, which would be astronomically heavier than the actual pipe. To find the true volume of a hollow pipe, you have to calculate the volume of the entire outer shape and then mathematically subtract the volume of the empty void inside it.
Wow.
You're essentially doing complex spatial geometry on the tailgate of a pickup truck before you even select which chains to use.
So once you've successfully mapped out the volume, figuring out how much three-dimensional space the object actually takes up, you have to multiply that by the density of the material.
Right. The material density is the multiplier.
And the sources provide these standard benchmarks that any safety professional or rigger just needs to have committed to memory. Like, steel sits at a massive 7,850 kilograms per cubic meter.
It's incredibly dense.
Yeah. Concrete is significantly lighter, relatively speaking, at roughly 2,400 kilograms per cubic meter. But then you encounter organic materials like wood, and the density suddenly becomes a massive moving target.
Oh, wood is a nightmare to calculate.
It varies wildly between 500 and 1,100 kilograms per cubic meter, according to the sources.
Yeah, and that variation in wood is a perfect example of why this discipline requires so much analytical rigor.
Because it's not standardized.
Exactly. Steel is manufactured to precise metallurgical standards. A cubic meter of structural steel in Tokyo weighs the exact same as a cubic meter of structural steel in Chicago.
Makes sense.
But wood is biological. It has cellular structures, it breathes, it retains varying levels of sap and moisture depending on exactly where the tree grew and how it was dried.
I want to push on that variance a bit because out in the field, materials are constantly exposed to the elements,
Oh, constantly.
Let's say you measure a massive wooden shipping crate that contains a delicate piece of machinery. The dimensions give you the volume, but that crate has been sitting on a loading dock in the pouring rain for 3 consecutive days.
It's soaked.
Right. The wood is acting like a giant sponge. how do you possibly account for the water weight? You can't just use the baseline density of 500 kilograms per cubic meter anymore.
No, you can't. And this is a scenario where standard math transitions directly into risk management.
Okay, how so?
Well, the Bechtel notes emphasize that when you are dealing with unknown variables like moisture absorption, a qualified rigger must default to the absolute worst-case scenario.
Oh, so you just assume the maximum.
Yes. You don't perform your calculations assuming the wood is dry pine. You run the math assuming the wood is completely saturated,
Sure.
pushing the density toward that maximum 1,100 kilograms per cubic meter mark.
You're purposely overestimating.
Exactly. You have to purposefully bloat your own calculations to build in a mathematical safety buffer.
So you are intentionally assuming the load is heavier than it probably is just to protect your equipment margins.
What?
Because if you calculate the lift, assuming the load is 10 tons, but the rain soaked into the wood and made it 12 tons, the crane's load computer is going to start screaming at you.
If you're lucky, it just screams at you.
Right. The crane doesn't care about your excuses regarding the weather. Gravity is an absolute constant.
And the margins for error are terrifyingly thin here. The engineering notes highlight a principle that should make anyone pause. Just a 5% error in calculating your volume leads directly to a 5% error in your total weight calculation.
Which doesn't sound like much.
5% sounds negligible in a classroom setting, sure. But if you are executing a critical lift near the crane's maximum capacity, underestimating the volume by 5% could easily push the physical weight over the crane's working load limit.
Wow. So a 5% error on a 100-ton lift means you just materialized 5 tons of invisible weight out of thin air. You've essentially hidden an entire adult elephant inside your math, and the crane is going to feel it the moment the load leaves the ground.
It's going to feel every pound of that elephant.
It completely recontextualizes why OSHA citations so frequently point to overloaded cranes as the root cause of fatalities.
It really does. But here's the thing. Weight alone doesn't tell you how a load will behave once gravity takes hold of it. Knowing the object weighs 100 tons is only the first piece of the puzzle.
Okay, what's the second piece?
The critical second piece is understanding exactly how that 100 tons is distributed across the physical dimensions of the object.
So you have to find the center of gravity, or the CG.
Right.
This is defined in the text as the exact singular point where the total weight of the object acts vertically downward. It's basically the perfect balance point.
Yes, the fulcrum.
If you could somehow hold a massive industrial generator on the tip of your finger, the center of gravity is the exact spot where your finger would need to be so the generator wouldn't tilt or fall.
That's a great visual. And finding that point requires moving past simple multiplication and into finding the weighted average of distances.
Which sounds complicated.
It can be. You have to imagine an axis running the length of the load. You take the weight of every individual component, say a heavy motor on one end, the lighter steel framing in the middle, and a delicate control panel on the other end.
Okay.
And you multiply each of those weights by their specific distance from a common starting point. Then you divide that massive number by the total overall weight of the entire unit.
So in a practical sense, for you listening and perhaps reviewing a lift plan, this means a complex piece of machinery almost never has its center of gravity perfectly in the physical middle.
Almost never.
If you have a 20-foot-long industrial skid and the massive diesel engine is bolted to the far left side, the balance point is going to be heavily shifted to the left.
Yes. And if the rigging team ignores the math, looks at that 20-foot skid, and simply places the crane hook dead center at the 10-foot mark, they're setting up a catastrophic failure.
Because it's not balanced there.
Right. The instant the crane begins to lift, the hook will naturally and violently seek to position itself directly above the true center of gravity.
I always picture moving a sleeper sofa.
Oh, that's a good one.
If you're helping a friend move a heavy couch and the fold-out metal bed mechanism is entirely shoved to one side of the frame, picking it up perfectly from the physical middle is a nightmare.
It really is.
One person is getting absolutely crushed under the weight of the metal mechanism, while the person on the other end is barely lifting the hollow armrest.
That analogy perfectly isolates the mechanical strain. In a rigging scenario, the person getting crushed is a steel wire rope sling.
Ouch!
When that load violently tilts to find its center, it throws an immense, unequal share of the overall weight onto just one or two slings. It creates a massive shock to the system.
And that's just the slings.
Exactly. Beyond the slings, an off-center load introduces what engineers call a side-loading hazard to the crane itself.
And cranes are architectural marvels, but they're designed to do one thing: pull straight up. Their entire structural integrity relies on vertical compression. They are shockingly weak when pulled horizontally. If an off-center load swings, it acts like a giant pendulum, dragging the crane boom sideways.
Which they are not built for.
That horizontal force can literally twist the boom out of its socket or pull the entire machine off its outriggers and just tip it into the dirt.
And the precision required to avoid this is just staggering. The engineering notes detail a specific real-world calculation for a complex skid where the true center of gravity was mathematically proven to be exactly 10.38 feet from the reference point.
Not roughly 10 feet.
No, not 10 feet. Not roughly 10 and a half. Exactly 10.38 feet. That single decimal point dictates the survival of the lift. The rigging team must configure their slings so the crane hook hovers directly over that 10.38 foot mark before a single ounce of pressure is applied.
But sometimes an object is so custom-built or its internal components are so dense and complex that calculating the center of gravity on paper just becomes a theoretical guessing game.
Yeah, paper plans only go so far.
You might have blueprints, sure, but maybe modifications were made in the factory that aren't on the drawing. How do riggers handle a load where the math is simply too convoluted to trust blindly?
The sources outline a fascinating practical solution for this. It's called the empirical center of gravity method.
Empirical meaning based on observation.
Exactly. It uses load cells, which are essentially incredibly sensitive, heavy-duty digital scales that you place between the load and the rigging.
Oh, that's clever.
You attach these load cells to the lifting points at both ends of the object. When you apply just a little tension, the digital readouts tell you exactly how much weight each side is bearing.
Like putting one foot on two different scales?
That's it. By taking the reading from the heavier side, dividing it by the total weight, and multiplying that fraction by the total distance between the two lifting points, you pinpoint the center of gravity using real physical forces rather than blueprints.
You're essentially forcing the object to confess its own balance point.
I love that phrasing, yes.
So we've mathematically proven the total weight. We've located the load's true center of gravity to the decimal point, and we've positioned the crane hook perfectly above it in empty space.
We are ready to connect.
The next phase is actually connecting the load to the hook using slings. And according to the Bechtel Rigging Handbook and the ASP prep materials, the geometry of these connections introduces the most dangerous mathematical trap on any job site.
It's where the most mistakes happen. The moment you introduce angled slings, you enter the realm of tension multiplication.
Tension multiplication.
Yes. The core equation dictating this is tension equals the total weight of the load, divided by the number of slings you are using, multiplied by the sine of the angle formed between the sling and the horizontal plane of the load.
Okay, hearing the word sine instantly triggers high school trigonometry anxiety for a lot of people.
Oh, for sure.
But understanding the physical behavior behind the math is absolutely crucial for anyone involved in safety. It boils down to this as the angle of the sling gets flatter, meaning it pulls closer to a horizontal line across the top of the load. The tension ripping through that sling increases at an exponential rate.
The engineering notes provide a tension factor table that illustrates this beautifully.
How does it break down?
Well, imagine a single sling dropping perfectly straight down from the crane hook to the load, forming a 90-degree angle.
Straight up and down?
Right. The tension factor is exactly 1.0. If the load weighs 1,000 pounds, the sling feels exactly 1,000 pounds of pulling force. But in industrial rigging, you almost never lift with perfectly vertical slings.
You can't usually.
No, you're usually reaching out from a central hook to the 4 outer corners of a massive box or a shipping container.
So for you listening, picture the slings forming a wide Y shape. From the hook, the cables angle outward to connect to the edges of the load. Because they are angled, those cables aren't just pulling straight up against gravity anymore.
No, they're pulling against each other.
Exactly. They are pulling horizontally against each other. The wider the Y gets, the harder the cables are trying to rip the load in half horizontally, which means they're fighting their own geometry.
And as that angle decreases from 90 degrees, the tension factor begins to climb. At a 60-degree angle, the multiplier becomes 1.15. Your 1,000-pound load is now exerting 11,150 pounds of tension on the rigging.
It's going up.
At a 45-degree angle, the factor jumps to 1.41. And this brings us to a universal, non-negotiable engineering rule mandated across OSHA and Bechtel standards.
What is it?
A rigger should never, under any circumstances, use a sling angle of less than 30 degrees.
And the math behind that 30-degree limit is terrifying. The sine of 30 degrees is exactly 0.5. When you divide by 0.5 in the tension equation, your tension factor hits exactly 2.0.
The force entirely doubles.
Right. If you're lifting a 10,000-pound object using 2 slings, and you spread them out so wide that they form a 30-degree angle with the top of the load, each individual sling is not holding 5,000 pounds.
Not at all.
Because of the extreme horizontal forces pulling against each other, each sling is experiencing a full 10,000 pounds of tension. By choosing a bad angle, you have magically generated more physical force inside the cables than the actual weight of the object itself.
The rigging is inflicting more violence upon itself than the load is. It's a profound concept.
It really is.
But let's ground this in reality. You're standing in the mud on a construction site, it's raining, excavators are roaring in the background, and you need to verify the tension on a set of slings before a critical lift.
You definitely don't have time to draw a triangle.
And you likely do not have a scientific calculator on hand to run sine functions either. So how do you ensure safety without the raw trigonometry?
The Bechtel rigging manual offers a brilliant, highly practical workaround known as the L/H method, or the field formula.
It's a lifesaver.
It completely bypasses the need for trigonometry. The formula states that tension equals the weight divided by the number of slings, multiplied simply by the sling length, which is L, divided by the vertical height from the load up to the hook, which is H. All you need is a standard tape measure.
It's so elegant.
Yeah.
You measure the physical length of the sling itself, then you measure the straight vertical drop from the hook down to the top of the load, divide the length by the height, and you have your tension multiplier.
It's a beautiful application of similar triangles geometry, translated into a blue-collar field hack.
Let's actually walk through this specific case study provided in the Bechtel sources. Imagine a rigging crew preparing to lift a massive 50-ton industrial module using 4 slings.
Okay, 50 tons.
A rigger throws a tape measure on one of the slings and finds it is 29.7 feet long. Then they measure the straight vertical distance from the crane hook down to the lifting lug on the module, which comes out to 25 feet.
Okay, so using the field formula, you take the length of 29.7 and divide it by the height of 25. That gives you a multiplier of roughly 1.18. You then take your 50-ton load, divide it by the number of slings to get the base weight per sling, and multiply by that 1.18 factor. Within seconds, standing in the mud, you have mathematically proven the exact physical strain your rigging is about to endure.
And you can verify if your equipment is rated to survive it. The goal is always to keep the rigging in the ideal safe zone of angles, which is between 45 and 60 degrees.
But you know, when you explain to someone that wider angles create exponential dangerous tension, human intuition often kicks in with a seemingly logical solution.
Oh, I know what you're going to say.
If tension is the enemy, just add more slings.
Right. Spreading the total weight across more connection points should universally reduce the strain on each individual cable, making the entire system safer.
It sounds perfectly logical.
It does. But the ASP blueprint notes completely dismantle that assumption. They expose what is arguably the most dangerous misconception in the rigging industry, the illusion of redundancy.
The illusion of redundancy. It's a great term. When a rigging crew uses a 3-leg or a 4-leg sling assembly to pick up a load, rigid body mechanics impose a brutally strict rule. The safety professional must calculate the tension, assuming that only 2 of those legs are carrying the entire burden.
It seems so counterintuitive. Why would you attach 4 massive steel cables to a load if the math demands you pretend 2 of them don't exist?
Right, why spend the money and the time?
The answer lies in the microscopic imperfections of physical reality. Theoretical math assumes perfect conditions, but we live in an imperfect world.
I always think of sitting at a 4-legged table in a restaurant.
Yes, the wobbly table.
Exactly. It is almost impossible to find a 4-legged table that doesn't wobble. Because the floor isn't perfectly flat, or one leg is a fraction of a millimeter shorter than the rest, the table is really only resting on 3 legs at any given time.
And if you lean on it?
All right, if you lean on it, the weight shifts diagonally across 2 primary legs, leaving one leg hovering slightly off the ground.
The rigid body physics of a suspended load behave exactly like that wobbly table. Because of tiny millimeter scale differences in the manufacturing of the wire ropes, slight stretching from previous lifts, or microscopic shifts in the center of gravity, a rigid load will almost never distribute its weight perfectly evenly across 4 distinct lifting points.
It's physically almost impossible.
Invariably, 2 legs situated diagonally from each other will snap taut and absorb the massive brunt of the weight. The other 2 legs are essentially just along for the ride.
Just acting as stabilizer.
Exactly, just acting as stabilizers to keep the load from spinning out of control.
So if a safety manager reviews a lift plan for a 40-ton generator, and the plan assumes that 4 slings will neatly share the burden at 10 tons apiece, that plan is functionally a death warrant.
It's incredibly dangerous.
In reality, 2 of those slings are taking 20 tons each. If the rigging crew selected slings that are only rated for 15 tons based on the flawed assumption of perfect distribution, those 2 load-bearing slings will catastrophically snap the moment the load clears the ground.
The entire system is genuinely only as strong as its weakest mathematical link.
And there's another massive, often overlooked factor that destroys lifting capacity. It's the physical geometry of how the sling wraps around its connection point.
The D to D ratio.
Oh, yes. The OSHA texts and BCSP materials dedicate significant attention to the D-DO ratio. This stands for the diameter of the load, which could be a shackle, a lifting pin, or a steel beam divided by the diameter of the wire rope sling itself.
This concept requires some vivid visualization for our listeners. Imagine a thick, incredibly stiff wire rope sling, maybe an inch in diameter.
Okay, pretty thick cable.
Now imagine taking that stiff wire rope and forcing it to bend sharply around a very narrow piece of metal, like a tiny shackle pin or the jagged edge of an I-beam.
Doesn't want to bend that way.
No, it doesn't. When you force a braided steel cable to make a tight radius turn, you generate devastating internal stresses within the rope itself. A wire rope is made of dozens of individual steel strands woven together. As it bends sharply, the strands on the outer curve of the bend are violently stretched to their tensile limit, while the strands on the inner curve are crushed and compressed against each other.
The text provides a chilling metric for this. If you have a D-DO ratio of 1:1, meaning the object you're wrapping the sling around is the exact same diameter as the sling itself, creating a violently tight bend, the physical lifting capacity of that sling is instantly reduced by a shocking 50%.
50%. Half of your structural integrity is completely wiped out.
And not by rust or wear and tear.
No, purely by bad geometry. You could have executed every other calculation flawlessly. You found the exact weight, you nailed the center of gravity to the decimal point, you established a beautiful 60-degree angle, and you accounted for the 4-leg redundancy rule.
You did everything right.
But because you hooked that massive wire rope over a pin that was too narrow, your rigging is only half as strong as the manufacturer's tag claims it is.
It perfectly illustrates why a safety professional must look at the lift as a holistic, interconnected ecosystem. You cannot just check off boxes on a form.
You have to see the whole picture.
You have to understand how the geometry of the connection points interacts with the tension of the angles and the reality of the weight. And the most terrifying part is that every single calculation we've discussed so far assumes a static universe.
Which doesn't exist.
Right. It assumes the load is frozen in time, sitting perfectly still like a photograph.
We have been calculating for a world without motion. But the instant the crane operator pulls back on the lever and the load breaks contact with the earth, the environment changes entirely.
Things get dynamic.
Very dynamic. We transition from static loads into the chaotic world of dynamic loads. And the governing law of physics abruptly shifts to Sir Isaac Newton's second law force equals mass times acceleration, or FMA.
Because loads in the real world are never perfectly still. A crane engine vibrates, the boom flexes, the hoisting cable bounces. Inertia fights against the upward pull.
Right.
To account for the kinetic energy introduced by movement, engineering calculations mandate the use of dynamic amplification factors, or DA.
We use the seatbelt effect to conceptualize dynamic force in our everyday lives.
It's the best way to understand it.
When you are sitting in your car waiting at a red light, your body exerts a static load on the seat. If you weigh 150 pounds, you are pressing 150 pounds of force downward.
Just resting.
But the moment you accelerate to 60 miles an hour and suddenly slam on the brakes, your body wants to keep moving forward at 60 miles an hour. When you hit the end of that seatbelt strap, you are no longer a 150-pound static load.
You are exerting hundreds of pounds of kinetic dynamic force against the fabric.
Exactly. The strap has to be engineered to survive the dynamic impact of your moving mass, not just your resting weight. The crane hook, the wire ropes, and the lifting lugs experience the exact same violent trauma when a crane operator jerks the controls or when a load slips and is suddenly caught by the rigging.
The Bechtel engineering notes quantify these dynamic amplifications with specific multipliers. If an operator executes a highly controlled, incredibly smooth lift, moving at a glacial pace, the safety calculations still require you to multiply the static weight by a def of 1.1.
You're adding 10%.
Yeah, you're adding 10% more weight to your math just to account for the micro movements of lifting. A normal everyday lift with standard operational speeds gets a def of 1.5. You are assuming the load is 50% heavier than it actually is.
But the numbers absolutely explode when you factor in a shock load.
What's a shock load technically?
A shock load occurs when there is a sudden, violent change in tension, like a load slipping a few inches before the slack abruptly runs out and the cable snap taut. The engineering notes state that a shock load multiplies the force by anywhere from 2 to 5 times the static weight.
That is insane. The math reality shared in the source material is staggering. Imagine a relatively light 500-pound piece of equipment.
Just 500 pounds.
If it slips during a lift, dropping just a short distance in free fall before the rigging violently catches it, the deceleration generates a dynamic force of 2,290 pounds.
In a fraction of a second.
In a fraction of a second, a 500-pound object generates nearly 1.25 tons of violent downward force. If a rigger selected slings rated for only 1,000 pounds because they thought they were only dealing with a 500-pound static weight,
that split-second shock load will instantly snap the wire rope like a thread.
And dynamic forces are not just vertical. They don't just come from up and down acceleration.
No, they come from all sides.
The most insidious dynamic force on a job site comes from the side, completely invisible to the naked eye. We have to account for wind load.
Wind is the great destabilizer of lifting operations. And the physics equation governing wind pressure is fascinating and deeply concerning. The formula states that wind pressure equals 0.00256 multiplied by the wind velocity squared.
The crucial element of that equation is that the velocity is squared. Wind force does not scale linearly.
It's exponential.
Right. If the wind speed simply doubles, the physical force it exerts on the side of your load doesn't double, it quadruples. If the wind speed triples, the force increases by a factor of 9.
And when you are lifting a massive flat object, like a solid steel plate or a concrete wall panel, it acts like a giant sail. The wind pushes against that massive surface area with geometrically increasing violence. And as it pushes, it causes the load to swing out and away from the crane.
Which brings us right back to the danger of the shifting center of gravity.
Exactly. Full circle.
When the wind pushes the load away, it moves the load's center of gravity further out from the base of the crane. This massively increases the overturning moment, the leverage the load has to pull the crane forward.
This exact chain of physical events is how massive multi-million-dollar cranes get tipped completely over into the dirt by a rogue gust of wind.
It explains why international regulatory frameworks are so intensely strict about weather conditions. The sources highlight port regulations in Egypt, which mandate a hard stop, a total cessation of all lifting operations if the wind speed exceeds just 20 kilometers per hour.
20 kilometers per hour is roughly 12 miles per hour. It is barely a brisk breeze.
It might rustle the leaves on a tree or mess up your hair slightly.
Yeah, but when that breeze is pushing against the massive sail area of a suspended cargo container, the squared velocity generates enough lateral force to cause a catastrophe.
Because gravity, geometry, and dynamic forces are so severe and the consequences of failure are so catastrophic, the equipment we use cannot be operated anywhere near its true physical breaking point.
We need buffers, massive buffers.
Right. We have to build massive, impenetrable walls of mathematical safety around everything we do. This brings us to the human element and the absolute necessity of safety factors.
Everything we have calculated today, the weight, the center of gravity, the angles, the dynamic shock, it all culminates in a single vital metric.
The working load limit.
Yes, the WLL. The WLL is the absolute maximum amount of weight you are legally and safely allowed to lift with a piece of equipment. And the equation to find it is working load limit equals the minimum braking load divided by a strict regulatory safety factor.
And the minimum braking load, or MBL, is a number derived from literal destruction.
They test it to failure.
Manufacturers take a wire rope or a chain into a laboratory, hook it up to massive hydraulic pulling machines, and stretch it until it violently snaps in half. If the chain shatters at exactly 40,000 pounds of force, the MBL is 40,000 pounds.
But we never, ever subject rigging to anything close to its minimum braking load in the field. We take that 40,000-pound destruction point and divide it by a safety factor to create a massive operational buffer.
What are the typical safety factors?
For alloy steel chain slings, the standard regulatory safety factor is 4-to-1. That means you divide the 40,000-pound breaking point by 4, resulting in a working load limit of 10,000 pounds.
Okay, so the chain is physically capable of holding 40,000 pounds, but you are only permitted to lift 10,000.
Exactly. The materials themselves dictate the size of the buffer. Wire rope, which has complex internal friction and hundreds of moving strands, requires a 5-to-1 safety factor.
A bigger buffer.
Synthetic nylon slings, which are incredibly strong but highly susceptible to being sliced by sharp edges or degraded by ultraviolet sunlight, have a safety factor ranging from 5-to-1 all the way up to 7-to-1.
Because they're more vulnerable.
Yes. But the most awe-inspiring mathematical buffer in the entire source text is reserved for personnel lifting.
When human beings are placed inside a basket and suspended hundreds of feet in the air from a crane hook, the mathematical safety margin just explodes. The required safety factor for personnel lifting is a massive 10-to-1 ratio.
It's huge.
If you weigh 200 pounds and you step into a suspended man basket, the rigging components holding your specific body weight must be physically proven in a laboratory to hold a full 2,000 pounds before they break.
It is a profound statement about the value of human life. We over-engineer the math by a factor of 10 because we refuse to tolerate even a fractional margin of error when flesh and blood are on the line.
However, all of these massive safety factors, all the 10-to-1 ratios and 5-to-1 buffers are built on a fragile assumption.
That the equipment is perfect.
Right. They assume the equipment is in perfect, pristine, factory-new condition. The math crumbles the moment the physical equipment degrades. This is why the OSHA guidelines and the Bechtel rigging handbook relentlessly hammer home the critical importance of brutal, uncompromising visual inspections before every single shift.
You cannot trust the tag if you don't trust the material.
Say that again.
You cannot trust the tag if you don't trust the material. The sources provide strict, objective criteria for when equipment must be thrown in the trash.
What are we looking for during an inspection?
Well, if a safety professional is inspecting a wire rope choker and counts more than 10 broken individual wires randomly distributed in one lay length that sling is dead, it must be destroyed.
Not just put aside, destroyed.
Destroyed. Cut it up so no one else can use it. The inspection criteria for synthetic nylon slings are even more visual. Manufacturers actually weave brightly colored threads, usually red deep inside the core of the strap.
Like a warning indicator.
Yes. If a nylon sling is dragged across rough concrete day after day, the outer jacket wears away. The moment those internal red warning fibers become visible to the naked eye, the sling has lost its structural integrity and must be removed from service immediately.
And what about the solid steel components, like the crane hooks themselves? Steel doesn't fray like nylon or snap into little wires like a cable, but it does deform.
Steel yields.
Right.
When a solid steel hook is subjected to a load that pushes it past its elastic limit, perhaps due to a massive unexpected shock load, the metal permanently stretches.
It bends.
The OSHA texts mandate that if you measure the throat opening of a hook and the jaw angle has increased by 15 degrees or more from its original manufacturer's specifications, it must be retired.
15 degrees isn't that much.
But that stretched jaw is physical proof that the molecular structure of the steel has been compromised. It will no longer hold its rated capacity, and it will eventually fail without warning.
The underlying philosophy here is constant vigilance. We are constantly monitoring the physics of the machine to protect the frail human bodies working around it. But, the source materials, particularly the ASP and BCSP notes, take a fascinating turn here.
They do. They pivot completely.
They shift their focus from the mechanical crane to the human body itself, introducing the NIOS lifting equation.
And the NIOS equation is used by safety professionals to assess the risks of manual lifts performed by human workers.
Like just picking up a box.
Right. And what is truly remarkable is that it applies the exact same mathematical rigor, the exact same geometric principles we use for a 200-ton crane to protect the human spine.
It calculates the recommended weight limit, or RWL, for a person picking up an object. It starts with a base load constant and then multiplies it by a punishing series of geometric variables.
You've got the horizontal multiplier, the vertical multiplier,
the distance multiplier, the asymmetric multiplier, the frequency multiplier, and the coupling multiplier. It's intense.
And when you break down those factors, the parallels to crane rigging are undeniable.
Let's hear it.
The horizontal multiplier measures how far the worker holds the box away from their stomach. In crane terminology, this is the exact same concept as the load radius.
Because the further away it is, the harder it is to lift.
Exactly. The further the load is from the center pin of the crane or the human spine, the less capacity it has.
And the asymmetric multiplier measures how much the worker twists their torso while holding the weight. That is the biological equivalent of sideloading a crane boom.
It's exactly the same force.
Twisting a human spine under tension shears the L4 and L5 discs the exact same way. A swinging lateral load violently twists the steel lattice of a crane boom. Whether the lifting machine is composed of steel hydraulics and wire ropes, or human bone, muscle, and cartilage, the physics of leverage and gravity remain absolute and unyielding.
That is the ultimate revelation of this whole topic. Rigging is not a game of estimating, guessing, or relying on brute strength.
It's math.
It is a deeply mathematical, intensely analytical, safety-driven discipline where gravity punishes ignorance instantly. From calculating the geometric volume to find the hidden weight, to mapping out the exact decimal point of the center of gravity, to mastering the trigonometry of sling angles and the explosive exponential threats of dynamic shock and wind velocity, true safety lives inside the calculations.
So for you listening, whether you are actively prepping to pass the ASP Domain 1 exam, or you are a safety manager who will be standing in the mud tomorrow morning reviewing a critical lift plan, resnect the math.
Verify everything.
Verify the working load limit against the actual conditions. Check those sling angles to ensure you are well above the 30-degree danger zone. Account for the invisible dynamic factors of wind speed and crane acceleration. You and your understanding of these formulas are the only safety check standing between a perfectly executed lift and a catastrophic failure.
Before we conclude our analysis of these sources, I want to pose a theoretical question based on the trajectory of our industry.
Okay, let's hear it.
The texts mention the integration of automated lift planning systems, like Bechtel's ALPS software. We are rapidly approaching an era where software algorithms and artificial intelligence become the default standard for calculating these incredibly complex matrices of wind pressure, exponential tension factors, and shifting centers of gravity.
The computer will just map the lift perfectly in 3 dimensions before a single cable is even attached.
It will do the math flawlessly in milliseconds.
Yeah.
But what happens to the intuitive, hard-earned, on-the-ground spatial awareness of the human rigger?
That's a good point.
If a tablet or an AI handles every complex variable, will the next generation safety professionals lose the fundamental ability to spot a critical, real-world geometric error with their own eyes?
If you don't use it, you lose it.
Right. The math might look perfect on an iPad screen, but if the rigger has lost the spatial intuition to visually recognize that a thick cable is bending around a dangerously sharp pin, destroying its D/D ratio, or that a sling is sitting at a lethal 30-degree angle, the perfect algorithm will not stop the load from falling.
It is the ultimate paradox of technological safety. We rely on the absolute precision of the software to make sense of a chaotic, muddy, wind-blown reality. But when you are standing under 50 tons of suspended steel and the wind begins to howl, you still need the visceral human understanding of the physics to know when the math on the screen no longer matches the reality in the air.
Absolutely.
Thank you for joining us on this QHSE Talks. Keep respecting the geometry, stay safe out there, and we'll catch you on the next one.